Uh, Folks, I'd like you to try number 11. Okay, in your groups, okay, working amongst yourselves, try number 11. Use the limit definition here. Folks, this is a particularly challenging one. Okay, ideally I'd have time to just say, hey, let's try this straightforward one. Okay, but we don't. Here's a particularly challenging one. What I need you to be able to do is get to here. If you can get to here, then you're getting started. Okay, that you understand the definition and how to apply it. Okay, then it's a question of, hey, do you know the specific trick to get through this specific problem? Okay? There are two ways you can do this. One is to get a common denominator for your two fractions and then combine it. Okay? I prefer to do it this way instead. Okay? I'm going to say that the LCD for all the small fractions would be 2 plus x plus h and 2 plus x. Sorry, folks. Some of you were looking at me a little crazily. I see that now. Okay. Do you see that this is the LCD here? Okay. So let me give you this example. If I gave you 3 over 4 plus 7 over 9 all divided by 2, what is the LCD for these two smaller fractions? It'd be 4 times 9, which equals 36. Do you see that? Okay, but I can't actually multiply those out, so I'll just leave it that way. Okay, so this is the LCD for these two small fractions. Okay? What I'm now going to do, let me just show you kind of straightforward. So we got 3/4 plus 7/9 all over 2. I'm going to now multiply this by 36 over 36. Right? Whatever happens in the denominator is what happens. In this case, I get 72. But in the top, look what happens. When I distribute this 36 to the first term, I'm left with 3 times 9. Because the 4 goes into 36 9 times, so I'm left with 3 times 9. And when I distribute the LCD to the second term, 9 goes into 36 how many times? 4, so I'm left with 7 times 4. Okay? Folks, if I lost you on that step, you gotta come by and see me. Okay? So let's do the same thing up here. I'm going to multiply this by 2 plus x plus h times 2 plus x all over 2 plus x plus h times 2 plus x. Let's do the denominator first. That's the more straightforward. It's just however the chips fall. So we get h times 2 plus x plus h times 2 plus x. And in the numerator, what happens? In the numerator, okay, so I want everyone to, once you get caught up, look up here, because I want to, it's a visual process. So take your time, but once you get caught up, look up here. You still copying it? That's great. Okay. Does everyone see how I got this line right here? I said I'm going to take this denominator and multiply it to h. Everyone okay with that? Okay. This is the hard part for some people to see. Okay. I'm now going to distribute this numerator to both terms. When I distribute the numerator to the first term, notice that these two factors cancel. Did I lose you? Raise your hand if I lost you. I got to know. Don't be afraid, but I got to know. Okay? When I multiply this numerator, I don't believe you guys. When I multiply this numerator to this term here, these two factors cancel. Okay? That's like, in my example, if I had 3 over 4 and I multiplied that by 36, which is my common denominator, what happens to those 4's? They cancel. Okay? So what am I left with? I'm left with 1 minus x minus h times this remaining factor of 2 plus x plus h. Oops, excuse me, 2 plus x. There's that minus sign. Here's this 1 minus x. Now, when I multiply this numerator to the second term, everyone take a look up here. When I multiply this numerator to the second term, it is these two factors that now cancel. Does everyone see that? Give me thumbs up, thumbs down, thumbs sideways. Okay? It's these two terms that cancel, so I'm left with 2 plus x plus h. Okay? Now I've just got a mess that needs to be cleaned up. I suspect by the time I'm done, I'll be able to cancel out the h. Okay? So foiling this out. Oops, and those cancel too. In this case, those two cancel. Okay. So things cancel. Okay. Folks, I need you to start compartmentalizing what I'm doing here. Okay. Up here, all I was doing was foiling things out and canceling them. Can you do that? Can you foil stuff out and cancel? Yes, you can. Okay. So maybe this would take you longer than it takes me, but just say, I know how to do that. And I need you to start saying, okay, now what are the steps that are confusing me? Okay. I know this is a big, long process. Okay. When things clear, we get the limit as h approaches 0 of minus 3 over 2 plus x plus h times 2 plus x. I can now evaluate this through direct substitution. I get minus 3 over 2 plus x plus 0 times 2 plus x, which equals negative 3 over 2 plus x quantity squared. That's how that cleans up. So folks, at this point, all tools that you learned in Chapter 2 are still up for, they're still fair game tricks to use. Okay, I did this one because I thought this one was particularly challenging. Okay? So I wanted to show you how to do it. Okay? Specifically, I choose to multiply both the numerator and the denominator by the LCD of the small fractions that showed up in this problem. Okay, the way I like to think of that is I like to say I am clearing out the smaller fractions. I'm clearing them out. Okay? Some of you might prefer a different route to doing this. I am fine with that. But I'm picking one method and I'm sticking with it. Okay? Yeah, Michael.
How do you get -3 on
Yeah, so this gave me -3h when I combined them. Right? And then the h and the... So I did skip one step here. At some point I would have had a -3h over h times all this stuff. And then I went ahead and canceled those h's. So that's how that -3 shows up there. So -2h minus another h gives me -3h. The h factor, though, cancels with this h in the denominator. Great question.
For some reason I kept reading negative, or -2 minus h plus 2.
Yeah, so it would be -2 minus 1, which is how we get the -3. Yeah. Yeah. So again, that's where you got to be careful. If you make mistakes with factoring, just be very careful with that before you do the canceling. Okay. All right. I want to talk to you about some other notation for derivatives. Okay. So if I give you the function f of x is equal to, it doesn't really matter, 3x minus 2. Okay. I could write its derivative as f prime of x. We've already seen this notation. This is called the prime notation. Okay? The prime notation is sort of a hybrid of a couple different notations that was developed over time. And it is the most condensed of the notations we use. So it's the one we show very often. Okay? Another notation for the derivative will be this. df dx. Okay? That symbol right there, df over dx, stands for the derivative. There will be times where that's the appropriate notation to use. It gives us the best lens to look at the problem. Okay? This notation right here is due to a fellow named Leibniz. Okay? And I think I've misspelled his name. Poor fellow. Leibniz. Okay? This is Leibniz's notation. Okay? The different notations become important in different stages in your calculus career. Okay? Most of us, as students, we're more comfortable with this notation because it's the first one I show you. And you look at this and you go, whoa. Don't. This says the derivative of f with respect to x. Altogether, the derivative of f with respect to x. This says the derivative of f. Okay? The only thing this adds is it adds that with respect to x idea. That's already leading where you'll go in a multivariate calculus class. You'll have derivatives with respect to other variables. Okay? There's one other notation. If I give you s of t is equal to 3t minus 2, here t is sort of understood to stand for time. Okay? Then especially in a physics class, you might see s dot t is the derivative. Okay? This dot notation is due to Sir Isaac Newton, and it's fallen by the wayside. Most people, it's still used in physics classes. It's rarely used in a math class. Okay? The dot specifically means that it's a time derivative. The derivative of s with respect to time. Okay? All right. Those are three notations. Oh. All right. So remember this function? Made you spend a lot of time learning how to work with limits with it, right? That's good, because now I want to talk about its derivative. Derivatives have limits in it. Okay? So where is this function differentiable? Okay? Well, let's look at the definition of the absolute value. It's just equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. Okay. So let's suppose x is greater than 0. Let's look at the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, this is equal to the absolute value of x plus h minus the absolute value of x all over h, and I've dropped my limit. Sorry about that. Now, h is approaching 0, right? So eventually it'll be a small quantity. What do we know about x? We're making the assumption that x is positive. Exactly. That's right. No, greater than 0. Okay. Greater than 0 plus a very small quantity will stay what? Greater than 0. Okay. Folks, this is very important. I'm talking in the air through this procedure, and a lot of you might take away from this, hey, you can just talk away the absolute value. Which is sort of what I'm doing, but I'm doing it in a very specific way. It's based upon the assumptions that we made. Okay? H will eventually get tiny. X is already positive, so a tiny number plus a positive number remains positive, which means I can go ahead and just use this definition of the absolute value, the one that says leave the stuff inside the absolute value alone. When this cleans up, we end up with just h over h, which is equal to the limit as h approaches 0 of 1, which is equal to 1. Now suppose that x is less than 0. Then we'll look at the limit as h approaches 0. Why am I picking this limit? Because I'm trying to find its derivative, right? This is the definition of the derivative of f of x plus h minus f of x all over h. This is the limit as h approaches 0 of absolute value of x plus h minus absolute value of x all over h. Now what is x?
Negative.
Some negative quantity. I haven't specified what it is, but it's a negative quantity. And when I add a very tiny number to a negative quantity, it stays negative. So I'm going to use the second of the two definitions. Let's see, this would then become plus x. Let me write it this way, though. It's minus from the formula, and then minus x. Which is equal to the limit as h approaches 0 of negative h over h, which is equal to the limit as h approaches 0 of negative 1, which is negative 1. Okay. I need just a tiny bit more room for this last part. Oh, let me go back and see this finished copy. Sorry. How we doing? All this stuff is coming back to haunt us from the first part, isn't it? Which is why reviewing your tests is a good idea. Okay.
So why did you use that again?
This definition? Yeah. So remember, which of these two rules do we do? When we're taking the absolute value of something, we either leave it alone or change the sign on it. If we know it's going to be positive, we leave it alone. If we know it's going to be negative, we change the sign on it. Okay? So from experience, I know that when I'm dealing with the absolute value, I break the problem into cases. Case 1, it's positive. Case 2, it's negative. X is negative.
So you just put a negative in front of wherever you see x from the original definition?
Well, I put close. I put a negative in front of the stuff inside the absolute value. So I didn't just put a negative in front of x, I put a negative in front of everything that was inside the absolute value. Right here, I'm talking about right here. So
Yeah.
there's x plus h. What did I do? I put a negative sign in front of all of it.
And we just switched it to parentheses.
Yeah, so the idea is if I ask you what is the limit, or sorry, what is the absolute value of 2 plus negative 5, okay, you could shortcut this by just saying, hey, this expression inside the absolute value, is it going to be positive or negative? What's it going to be? It's going to be negative, so what I could do is just put a minus and then rewrite the expression. When I simplify that, I'll have minus, and then this gives me negative 3, and I end up with 3, which is what you would get if you did the long way around the barn and just simplified, right? This would be 2 plus negative 5 is negative 3. Absolute value of negative 3 is positive 3. So the idea is if you already know what the expression inside the absolute is going to be in terms of sign, you can just recopy the expression and then put either a plus sign here or a minus sign here. Michael?
So just essentially that's how we pull our function out of the absolute value in order to solve it for less than 0 over 0.
Exactly. So generally, when you're working with an absolute value, you get to those absolute value marks and you're stuck. Unless you can break it up into cases and say, let's assume it's going to be positive, then this would be the case. Let's assume it's going to be negative, then this would be the case.
So that's the reason why that first step's pretty important, right?
This part right here?
The piecewise function.
Yes, that's why understanding the piecewise function is essential to doing these problems. Yes, absolutely. No fun. Okay. All right, let's, I know we're about out of time here, folks, but I want to finish this story, okay? I don't want to leave you hanging. So finally, at x equals 0, I'm going to return to the pointwise definition, because here I'm assuming x is a specific value. Let's return to the pointwise definition of the derivative. Okay? I would have the absolute value of x minus 0 all over x minus 0. But what do we know about this limit? It was one of your test questions. This limit does not exist. Because remember your test questions, I have you find the left-hand limit, and the left-hand limit's -1. I have you find the right-hand limit, the right-hand limit's +1. They disagree with each other, so this limit does not exist. Okay. Let's put that all together on the graphs. Okay? So I know I'm going over by a few minutes, folks, but this is oh so important. Okay? What does the graph of the absolute value function look like? For positive values, it's just the identity. And for negative values, it's the opposite of the identity. Okay? What should the derivative do? The derivative should tell us the slope of the tangent line at any point along here, right? If I put a point right here and ask you what's the slope of that line, what is the slope of that blue line? That slope is -1. What if I move it over just a little bit? What's the slope of that blue line? Still -1. What if I put it here? +1. What if I put it here? Okay. So what we find is that the graph of the derivative of the absolute value function looks something like this. Now, go ahead and try and put a tangent line at this corner right here. Try. Is this the tangent line? Or is that the tangent line? Or is that the tangent line? None of them work. Can I draw a tangent line at that sharp corner? No. So what has to happen? The derivative is shown not to exist at x equals 0. And we see that when we tried to find the derivative pointwise. It did not exist there. Again, we were doing this problem for a reason from the get-go. So, all that said, you cannot always find the derivative at points in a function. There's going to be 3 reasons why you can't, and here's one of them. We have a corner there. Okay, we've already seen one other example, but we'll talk about that more next time. Folks, go ahead and jump into your homework with this. Okay, please, please, please I feel like I haven't seen folks in office hours recently. I've been twiddling my thumbs.
Thank you.
Just sitting there with nothing to do. Hoping you guys come by with questions. All right, I'll see you next time.